Now, there's four ways we can think about dropping a ball, right? We can either use energy calculations, we can use Suvat equations, we can use our force explanation, and then lastly, we can use a little bit of differential calculus. Obviously, there's a fifth interpolation of Einstein's theory of general relativity, but that itself is more of a... I don't know how to explain that one, basically. I'm not going to preach that I'm a genius here. But here are the four ways we can think about dropping a ball. The first one we're going to deal with is energy calculations. I'm going to hand it over to my boy Harsh, a fellow maths tutor who enjoys teaching maths. I dropped the pen again.
So, we've dropped a 5 kilogram ball down a 50 meter building, and we're wondering what's its final speed going to be. It's a really heavy ball, and I have no idea why we're doing this, but this is our situation. How would we go about solving for this? At the start, we know that our ball has potential energy. We'll call it E pot. And what is that equal to? mgh, which is given by our formula for work, which is force times displacement. And what is force? Force is mg. Gravity. What's displacement? H. So this is equal to mgh. And potential energy is just the potential for the gravitational field to do work on our system. And we know at the start that E kinetic at the start is equal to 0. And we know that at the end, our potential energy is equal to 0, and our kinetic energy is given by a half mv squared. And we know that the energy at the start has to be equal to the energy at the end. This means our starting potential energy is equal to the kinetic energy at the end, the conservation of energy. And so then we get mgh is equal to a half mv squared. Immediately, I can tell m's cancel. And so thus we get that gh is equal to a half v squared, which then means 2gh is equal to v squared, which then means that root 2gh is equal to v. And we know that g is 9.81 and h is 50. So 2 times 9.81 times 50 times 50, and I erased way too much. 2 times 9.81 times 50 is equal to v. And what's that equal to? 31.3 meters per second. That is approximately 100 kilometers an hour. I will now pass this back to Thyssen so that he can solve for the time it takes for the ball from the start of the fall to reach the ground.
Thank you for your wonderful explanation, Harsh, of the main problem that we have. Here we have a ball and we're dropping it from 50 meters. Our job is to now find the time it takes for it to hit the ground. So let's just say this is our ball. It's hit the ground. It's going to hit the ground, right? And the first thing we distinguish is the diagram. What does the diagram look like? Well, we know that it's going to be 50 meters high. We're going to have u equals 0 because the initial velocity is 0. And then last thing, we're going to pick our direction of motion. Now I'm going to pick the direction of motion as down here. Why am I picking it as down? Well, picking it as up just makes everything negative and kind of hard to deal with. So we're going to pick down because it's the more intuitive approach. So down is our direction of motion here. How can we think about this after we've set out all this information? How can we find out, well, what time it hits the ground? Well, assuming constant velocity, that only gravity is acting on it, we use the equation S equals ut plus a half at squared. Now then, let's think of what each of these means. So S refers to the displacement. The displacement it will travel when it goes from here all the way to down here is going to travel a displacement of 50 meters. So we're going to put 50 here. Now we've already said that the initial velocity of the ball is 0, so that means this whole thing, ut, is just going to be 0 because 0 times anything is just 0. And then we add here a half. What is our acceleration? Our acceleration is due to gravity. If we think about our acceleration constant, we can either use 9.8 or 9.81. Now, because the VC uses 9.8, we're going to use 9.8 here. And then last of all, we have t squared. So if we do a little bit of arithmetic, we realize that 50 is equal to 4.9 t squared. And from here, this is just simple rearranging. Now, if you're insane, you can use quadratic formula. If you're me, you can simply just rearrange for t. So here we divide both sides by 4.9. So we get a 50 divided by 4.9 equals t squared. Right? And from here, right, we get our final answer of t equals plus or minus the square root of 54.9. Now, my dog just walked into my room. That's why you hear scratching. Get over here, buddy. Get over here. Oh, this is my dog. So we're given a plus or minus solution here. How do we pick between the positive solution and the negative solution? Well, here we're assuming that time doesn't actually go backwards, so we're going to pick the positive solution because from here it starts off at t equals 0, and down here it goes to t equals, well, 1. I mean, not t equals 1. T equals the square root of 50 divided by 4.9. It's not going up, it's going down. So here our final answer is actually going to be t equals the square root of 50 over 4.9, which is approximately 3.17 from my calculations. So I'm going to pass it back to Haas to speak about the force calculations that we're going to do on a non-linear an object which experiences air resistance.
Level 3. Now we want to consider the forces acting on the ball as it falls down the building. So imagine this is our ball. There's one very obvious force involved. That's gravity. And that's downwards. And it's given by mg. But then there's also an upwards force that you will almost have never touched in physics. Air resistance. And we shall assume that it's not negligible in this case. What is air resistance given by? Fr is given by k times the velocity squared. And since it's a resistive force, it goes opposite to our direction of motion, which means it works upwards. And since we know our air resistance is proportional to v squared, and that v keeps increasing as we fall, eventually Fr will equal mg. And this is actually a time where we will stop accelerating and achieve terminal velocity, which is a term you might have heard. It simply means it's the fastest speed we can go from just falling in free fall. As beyond that, our air resistance is stronger than gravity. And we can solve for this. We can simply say that kv squared is equal to mg. And then we can say that v squared is thus equal to mg 1k. And so thus v is equal to the square root of mg over k. And we can use this to solve an equation. And that equation is a second order nonlinear differential equation, which I'm not going to touch. And that I will give back to Thyssen to solve.
Harsh has explained our force calculations, how we understand forces, how we use forces, and how they can describe, well, what our differential equation is going to be. So here, as Harsh said, we know that the sum of the forces here, we use sigma to denote sum, is going to be mg, which is the gravitational force acting on the object, take away v squared times k, where k is just some arbitrary constant. So now, if we remember that F equals ma, so we can rewrite this equation as ma equals mg take away kv squared, right? And now we can just rearrange. We can create our differential equation in two ways. We can either do realize that a is the same thing as dv over dt, or we can say a is da squared, d squared x over dt squared. That took me a bit of time to figure out. But we can either write dv, we can either replace a for dv over dt, solving a first order differential equation, or the second order one that Harsh talked about, d squared x over dt squared. And let's write out the first order one because that's the one I'm going to be dealing with. So here we have it m times by dv over dt equals mg take away kv squared. We divide both sides by m, dv over dt equals g take away k v squared over m. Because k and m are both arbitrary constants, it doesn't actually matter what value they take up. So here we can actually we can remove m completely by instead using a different integration constant. So here we're just going to do kv squared. Now, I know that means like k over m equals k. They aren't the same k. We'll denote this one as k1, and we're going to denote this top one here as just regular k, because that's the one we're going to be working with when we're actually solving the differential equation. So then we get our final differential equation: dv over dt equals g take away kv squared. And we're going to use that as well as our next differential equation. Once we've differentiated this and found it in terms of v, we're going to use that v equals dx over dt to find out what our displacement equation is going to be for this differential equation we've been given. Now the conditions, I'm going to label them now. We're going to have the velocity when it's the time is equal to 0 equaling 0. We have the velocity at t equals 5 equaling 10. And we also have here that x equaling 0, x equals 0, x of t, right, equals 0, because when it initially starts off, it hasn't fallen any distance, it hasn't changed any positions, it hasn't moved anywhere, it hasn't done anything. So here, these are our three initial conditions, which helps us find what this k value is, our first integration constant when we rearrange this one, and our second integration constant when we do that again for this one. Now I've created a small animation to show this one off and how we actually go about doing this differential equation. But basically, we'll get a solution from it, and we'll get our final answer, which I will explain once we've gotten to it. Okay, well, now we're back after that small little animation bit there. So we see that we get a final answer of approximately 5.17, and well, we can see it's going to be slower. As we remember, our SUVAT calculation gave us a value of the square root of 50 divided by 4.9 square rooted is equal to, in this case, 3. Can the camera see that? The calculator can you can see it. It's 3.19 there. And what we got as our when we solved this differential equation is we got an answer of around 5.17. Now obviously this will change depending on the initial conditions that we use, and well, the k value that we get, because here the k value is a bit weird to solve. Here I actually use Newton's method to solve the k value. You can also use a more graphical solution, or if you really wanted to, you could just put it into Wolfram Alpha, because that's what one of my friends insisted I did, instead of just using Newton's method. So that's how we solve this differential equation. And I want to explain this differential equation a little bit more. How does this differ from our SUVAT calculation? Why does it differ from our SUVAT calculation? Well, in our differential equation approach, we've assumed that air resistance isn't constant. So we can't use the SUVAT equations, because one requirement for the SUVAT is that the acceleration is constant. Here, it depends on v squared, and v squared is constantly changing. Hence, it's not going to be constant. This also affects our energy calculation, because as we remember, if F equals mg take away kv squared, we need to remember that the work done on the object is going to be mg take away kv squared times by d. So in Harsh's initial case, he's actually assuming that there's no air resistance there either, which is why we get a different answer here compared to our first couple of solutions. This is why we need to remember that our world actually doesn't work in linear ways. We don't really work with linear systems too much. Here, this is a differential equation, right? This differential equation is non-linear. It changes all the time. And sure, we can use our basic energy calculations to explain, those small little itty-bitty changes. But now we have to employ differential calculus when we want to get more accurate answers to our solutions in this case. So I hope you enjoyed this video. I would like to thank Harsh for coming on to this video. I really enjoyed making the video with him. I did yap to him a little bit. I was like, damn, this shit is gonna be fire. Anyway, I hope you enjoyed the video, and I hope you enjoyed the understanding that we got from going through physics, specialist maths, and a little bit of calculus too. I hope to see you later, and have a good day.